Imagine a place in the universe where gravity becomes so powerful that even light cannot escape. No matter how fast you travel, no matter how bright you shine, once you cross a certain boundary, the universe itself seems to close behind you. These objects are called black holes. They are invisible, yet they shape entire galaxies. They bend light, distort space, and can release more energy than billions of stars combined. But here's the real mystery. Why do black holes exist at all? What process in nature allows matter to collapse so completely that it creates a region of space where escape becomes impossible? In this video, we're going to journey across the universe to uncover the answer. From the tiniest structures of matter, to the life and death of massive stars, to the gigantic black holes hidden at the centers of galaxies. And along the way, we'll discover that black holes are not just cosmic monsters. They may be one of the universe's most profound clues about how space, gravity, and reality itself truly work. Black holes are among the strangest objects the universe has ever created. They are regions of space where gravity becomes so powerful that nothing, not even light, can escape their pull. Imagine a place where the rules of nature seem to stretch to their absolute limits. A place where space itself curves inward like a cosmic whirlpool. For centuries, humans looked up at the night sky and saw stars shining across the darkness. Yet hidden among those stars are objects that produce no light at all. They are invisible, silent, and almost impossible to detect directly. And still, their presence shapes the universe around them. It sounds almost unbelievable at first. How could something become so dense that even light, the fastest thing in existence, cannot get away? What kind of cosmic process could compress matter so completely? The answer begins with one of the most familiar forces we experience every day: gravity. Here on Earth, gravity is what keeps our feet on the ground. It pulls rain toward the soil, keeps the oceans from floating away, and guides the moon around our planet. But gravity has another side, one that appears when enormous amounts of matter gather together. Under the right conditions, gravity doesn't just hold things together. It can crush matter inward with unimaginable force. And when that happens on a truly colossal scale, something extraordinary can form. To understand how that happens, we first need to see how scientists discovered black holes hiding throughout the universe. And surprisingly, they reveal themselves in ways you might not expect. For something that cannot be seen directly, black holes leave surprisingly dramatic fingerprints across the universe. Astronomers rarely observe a black hole itself. Instead, they watch the strange behavior of the objects around it. And those behaviors reveal that something enormous and invisible is lurking nearby. One of the first clues comes from stars moving through space. In some regions of the galaxy, astronomers observe stars orbiting around empty-looking points. There is no visible star at the center, no glowing cloud of gas. Yet the stars move as if something incredibly massive is pulling on them. It's a bit like watching leaves swirl around a hidden whirlpool in a river. You may not see the spinning water clearly beneath the surface, but the motion of the leaves tells you something powerful is there. In space, the leaves are stars, and the hidden whirlpool is gravity. Even more dramatic signs appear near the centers of galaxies. There, astronomers observe enormous jets of energy blasting into space at nearly the speed of light. These jets stretch across thousands of light years, like cosmic searchlights piercing the darkness. The only engines powerful enough to produce them are supermassive black holes. And then there are the ripples in space itself. When two black holes collide, they send gravitational waves racing across the universe. These waves slightly stretch and squeeze space as they pass through Earth, which raises an even deeper question. What kind of matter could collapse enough to create such objects in the first place? To answer that, we need to travel far deeper, all the way down to the smallest structures of matter itself. To understand how something as enormous as a black hole can form, the journey surprisingly begins at the tiniest scales of matter. Everything in the universe, stars, planets, and even human beings, is built from atoms. At first glance, atoms might seem solid and compact, but in reality, they are mostly empty space. At the center of every atom sits a tiny nucleus made of protons and neutrons. This nucleus is incredibly dense compared to the rest of the atom. If an atom were the size of a football stadium, the nucleus would be smaller than a marble at the center. Yet almost all the atom's mass would be packed inside that tiny point. Normally, powerful forces inside the nucleus keep matter stable. These forces act like microscopic glue holding protons and neutrons together. They balance against other forces that try to push particles apart. In everyday conditions, this delicate balance keeps matter from collapsing inward. But the universe does not always stay gentle. In extreme environments, such as the collapsing core of a massive star, gravity begins to push matter closer and closer together. Atoms can be crushed so tightly that their electrons are forced into the nucleus. Matter begins to transform into strange and incredibly dense states. Imagine squeezing a snowball in your hands. As you compress it, it becomes smaller and harder. Now imagine gravity doing something similar to matter, but with pressures billions of times stronger. Under such conditions, even the forces inside atoms may struggle to resist gravity's pull. And when gravity wins that battle, matter can collapse far beyond anything we see in ordinary objects. But to understand how this collapse begins, we first need to look at a much larger stage, the world of planets, moons, and massive bodies shaped by gravity. Gravity is the quiet architect of the universe. It gathers dust into rocks, rocks into planets, and planets into entire worlds. Every time matter collects in one place, gravity grows stronger, and slowly, that invisible pull begins shaping the structure of the cosmos. On a small object like an asteroid, gravity is weak. A person standing on its surface could almost float away with a single jump. But as objects become larger, like planets, their gravity becomes much more powerful. Suddenly, everything begins to pull inward toward the center. This inward pull is why planets become round. Mountains, oceans, and landscapes may decorate the surface. But deep underneath, gravity is always trying to compress the planet into a sphere. It's like squeezing a ball of clay until it becomes perfectly smooth. The same principle applies to stars, but on a far more extreme scale. Stars contain enormous amounts of mass, sometimes millions of times heavier than Earth. Inside them, gravity constantly presses inward, while nuclear energy pushes outward. For most of a star's life, those two forces balance each other perfectly. But balance in the universe is rarely permanent. Eventually, stars run out of the fuel that supports them against gravity. When that happens, gravity suddenly has nothing pushing back, and the entire star can begin collapsing inward under its own weight. It's a collapse far more dramatic than anything that happens to planets. Imagine an ice skater pulling their arms inward and spinning faster and faster. As the star contracts, its gravity becomes stronger and stronger. And in the most massive stars, this collapse can spiral into something extraordinary, something so extreme that it leads directly to the creation of a black hole. But how do scientists detect something that emits no light at all? The answer lies in the tools humanity has built to observe the universe itself. Even though black holes cannot be seen directly, scientists have learned to detect them by watching how they affect their surroundings. It's a bit like spotting the wind by watching trees sway or flags ripple in the air. The wind itself is invisible, yet its influence is unmistakable. Black holes reveal themselves in much the same way. One of the clearest signs appears when gas and dust fall toward a black hole. Instead of plunging straight in, the material begins spiraling around it. This swirling structure is called an accretion disk, and as the gas spins faster and faster, it heats up until it glows intensely. In fact, some of the brightest objects in the universe are powered by black holes. When matter in the accretion disk becomes extremely hot, it releases enormous amounts of energy. These glowing disks can shine brighter than entire galaxies. Ironically, the darkness of a black hole often creates some of the universe's brightest light. Another remarkable phenomenon is gravitational lensing. Because black holes bend space itself, they can distort the path of light traveling nearby. This bending effect acts like a giant cosmic magnifying glass. Distant stars and galaxies may appear stretched, curved, or duplicated in strange arcs. In 2019, humanity achieved something once thought impossible. Using a global network of telescopes called the Event Horizon Telescope, scientists captured the first image of a black hole's shadow. The glowing ring surrounding the darkness revealed the silhouette of a supermassive black hole. For the first time, the boundary of one of these cosmic monsters had been directly observed. But seeing a black hole's shadow only deepened the mystery. What kind of physics could create a region where even light cannot escape? To answer that, we must step into one of the most revolutionary ideas ever proposed about the universe. An idea that completely changed our understanding of gravity and space itself. To truly understand black holes, we need to rethink what gravity actually is. For a long time, gravity was imagined as a simple pulling force between objects. But in the early 20th century, a revolutionary idea changed that picture forever. It revealed that gravity is not just a force, it is the shape of space itself. According to the theory of general relativity, massive objects bend the fabric of space-time. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet curves downward around the ball. Now roll a marble nearby, and it will spiral toward the dip. Planets move around stars in a similar way. They are not being pulled by invisible strings. Instead, they follow curved paths through warped space-time. Gravity is simply the motion of objects following those curves. But what happens when an enormous amount of mass is squeezed into a tiny region? The curvature of space-time becomes more and more extreme. The dip in the cosmic fabric deepens until it becomes a kind of bottomless funnel, and eventually something remarkable appears. A boundary forms around this funnel called the event horizon. Cross that boundary, and escape becomes impossible. Even light, the fastest thing in the universe, cannot climb out of the curved space-time inside. Beyond that horizon lies the region we call a black hole. Yet this raises an even deeper question. What kind of cosmic events could compress so much mass into such a small space? To find the answer, we must look at the life cycles of stars themselves, and the dramatic endings that some of them experience. Long before black holes captured the imagination of astronomers, scientists were already studying a much gentler form of gravitational collapse. The formation of stars and planetary systems begins inside enormous clouds of gas and dust drifting through galaxies. These clouds, called nebulae, may stretch across dozens of light years. At first, they appear calm and almost motionless in the darkness of space. But gravity is always at work, even when it seems subtle. Tiny regions inside the cloud begin gathering slightly more matter than their surroundings. Once that happens, gravity slowly pulls more gas toward those regions. Little by little, the cloud begins collapsing inward. As the cloud contracts, it starts spinning faster. The process is similar to an ice skater pulling their arms inward during a spin. As the radius shrinks, the rotation speeds up dramatically. The collapsing cloud eventually flattens into a rotating disk. At the center of that disk, matter piles up until temperatures rise high enough to ignite nuclear fusion. A new star is born. Around it, leftover material forms rings of dust and gas. Over millions of years, those rings clump together to form planets, moons, and asteroids. Our own solar system formed this way about 4.6 billion years ago. The sun ignited at the center while planets slowly assembled from the surrounding disk. Most stars in the universe experience similar births and stable lives. Gravity pulls inward, but nuclear energy pushes outward, creating balance. But not every star is able to maintain that balance forever. Some stars are so massive that their final moments become extraordinarily violent. When their nuclear fuel is gone, gravity takes complete control. And in those catastrophic endings, the conditions for black hole formation can finally appear. At first glance, black holes might sound like cosmic monsters wandering through the universe and swallowing everything nearby. But in reality, Earth is not in any danger from them. The nearest known black holes are thousands of light years away. On cosmic scales, that distance is incredibly safe. Still, black holes influence the universe in subtle but powerful ways. They help regulate the growth of galaxies and the birth of new stars. In some regions, energy from black holes can heat enormous clouds of gas. That heating can either trigger star formation or prevent it entirely. This influence often comes from the energetic environments surrounding black holes. When matter spirals into a supermassive black hole at a galaxy's center, huge amounts of energy are released. Jets of particles can shoot outward for thousands of light years. These jets can stir and reshape the gas spread throughout a galaxy. In a sense, black holes act like cosmic engines. They redistribute energy across enormous distances. Some astronomers even think they help prevent galaxies from forming too many stars too quickly. Without this balancing effect, galaxies might evolve very differently. Even here on Earth, black holes have contributed to scientific breakthroughs. The detection of gravitational waves in 2015 came from the collision of two distant black holes. Those waves traveled across the universe for more than 1 billion years before reaching our detectors. For the first time, humanity could hear the ripples of space-time itself. Discoveries like these remind us that black holes are not isolated curiosities. They are deeply connected to the structure and evolution of the cosmos. And nowhere is that connection more dramatic than at the hearts of entire galaxies. Because at the center of many galaxies, something truly enormous is hiding. When astronomers began studying the centers of galaxies, they discovered something astonishing. Hidden deep within many galaxies lies an object of unimaginable mass. These objects are not ordinary black holes formed from collapsing stars. They are supermassive black holes, millions or even billions of times heavier than the Sun. At the center of our own galaxy, the Milky Way, such a giant exists. Astronomers have tracked stars orbiting around an invisible point called Sagittarius A. These stars move at incredible speeds, completing their orbits in just years or decades. Only something extremely massive and compact could produce such powerful gravity. Watching these stars is a bit like observing leaves spinning around the drain of a giant cosmic whirlpool. The whirlpool itself cannot be seen directly, but the motion of the leaves reveals the powerful pull beneath the surface. In the same way, stellar orbits reveal the hidden presence of supermassive black holes. These giants are not just passive objects sitting quietly at galactic centers. When matter falls toward them, enormous amounts of energy can be released. Entire galaxies can light up as quasars, brilliant objects powered by feeding black holes. For a time, they can outshine every star in their host galaxy combined. Scientists now believe that supermassive black holes and galaxies evolve together. As galaxies grow, their central black holes grow as well. The energy they release may influence how stars form across the galaxy. In a sense, the heart of a galaxy helps shape the entire structure surrounding it. Yet this discovery leads to an even deeper mystery. How did these enormous black holes become so massive in the first place? Some of them appeared very early in the universe's history. To understand that puzzle, we must travel all the way back to the beginning of the cosmos itself. To understand the deepest mystery of black holes, scientists look far beyond individual stars or galaxies. They turn their attention to the earliest moments of the universe itself. Just after the Big Bang, the cosmos was a dense, hot ocean of energy and particles. Everything that exists today emerged from those first chaotic moments. As the universe expanded and cooled, matter began to gather into the first structures. Tiny fluctuations in density, barely detectable differences in matter, slowly grew under gravity's pull. Over millions of years, these small variations turned into vast clouds of gas. Eventually, the first stars ignited within them. Many of those early stars were far larger than most stars we see today. Some may have been hundreds of times more massive than the Sun. Because of their enormous mass, their lives burned quickly and ended violently. When they collapsed, some may have formed the universe's first black holes. But that may not be the whole story. Some scientists propose that black holes could have formed even earlier. In the intense conditions of the young universe, regions of matter might have collapsed directly under gravity. These hypothetical objects are known as primordial black holes. If they exist, primordial black holes would have formed only fractions of a second after the Big Bang. They could range in size from microscopic objects to massive cosmic bodies. Some researchers even wonder whether they might contribute to the mysterious dark matter in the universe. If true, black holes could be woven deeply into the fabric of cosmic history. Over billions of years, black holes continued growing through mergers and by swallowing nearby matter. Small black holes combined into larger ones, gradually building the giants seen in galaxies today. In this way, their growth mirrors the growth of the universe itself, which leads to a profound realization about what black holes truly represent. Black holes represent one of the most extreme outcomes nature can produce. They are places where gravity overwhelms every other force we know. Matter collapses inward, light cannot escape, and space-time itself bends into a deep cosmic well. In many ways, black holes are the ultimate expression of gravity's power. Yet they are not simply destructive voids scattered across the universe. They are part of the cosmic story of creation and transformation. Stars are born, galaxies evolve, and sometimes matter collapses into these extraordinary objects. Black holes are woven into the life cycle of the universe. What makes them even more fascinating is how they challenge the limits of human knowledge. At the center of a black hole lies a region called a singularity. In that place, our current laws of physics can no longer fully describe what happens. It is a boundary where our understanding of nature reaches its edge. Throughout history, humanity has always been drawn toward mysteries like this. From ancient stargazers to modern astronomers, People have looked upward, searching for answers. Black holes remind us that the universe is far stranger than our everyday experiences suggest, and that many of its secrets are still waiting to be discovered. In a way, black holes are not just objects in space. They are signposts pointing toward deeper truths about the cosmos. They reveal how far gravity can shape reality and how much we still have to learn. And perhaps most importantly, they remind us that curiosity itself is part of humanity's journey through the universe.